staircase function. Okay, are you ready? Yes, your microphone is closed.
Okay, perfect. I just only have to share it. Sorry for the disturbance. Well, thanks a lot to everybody who is present in these conferences. I am very happy. And thanks a lot to Professor Ramirez Arellano for giving us the opportunity to give these conferences. Firstly, as Professor Mike Porter specified, the Mayan calendar is very special because it has several cycles. The most important one, the one we're celebrating today, is the calendar round, which corresponds to 52 solar years. Well, it also has 18,980 days. It also corresponds to 73 cycles of 260 days. Those cycles are very special because they are very close to the normal human pregnancy. It also contains 32.5 Venus cycles and 2 human generations. Of course, by human generations, I understand, well, we understand what we nowadays call the baby boomers, the Generation X. I am a Generation X. The millennials, the Generation Z, and the Coroners. That is those who are born or who are spending their infancy in this pandemic. Okay. Talking about the first time that I met Professor Ramirez de Arellano, I have to say that I arrived to the Department of Mathematics in February in '92, after obtaining my master's degree in electrical engineering. I was enchanted, well, after I finished my master's degree in electrical engineering, I was enchanted by a very big problem in complex analysis, that is by the problem of a removable singularity for holomorphic functions, which is related to the general topology and complex analysis. My reception in the Department of Mathematics was mixed because, not because I was 20 years old at that time, but because I have a master's degree in electrical engineering. In the 70s, it was very common that the students will switch careers from electrical engineering to mathematics, but for the 90s, when I arrived to Simvestab, it was not very common. So I received a mixed reception here. But in this case, I am very grateful with Professor Ramirez de Arellano because he was very kind with me when I arrived to the Department of Mathematics. And he actually taught to me my first course in complex analysis. Well, my first formal course, because usually I only read books and some papers in complex analysis. And in memory of those days, that is when I arrived to the Department of Mathematics and I was more interested with complex functions of uncomplex variables, I will want to give this conference in the name, well, with the subject of removable singularities. So let me begin with a very nice result, which was just published by Professor Chirka, well, just published 5 years ago, which saying that we have a closed subset of a Riemann surface, the classical Riemann surface of dimension 1. And we take a meromorphic function, well, a function which is meromorphic in the exterior of a closed subset, such that it satisfies 2 conditions. First, for each point, the cluster set is connected and has connected components. The cluster set is obtained by taking all the sequences which are converging to a point, well, this point set in the cluster set, and observing what happened with the sequences, well, with the, sorry, with the sequences in the image, that is after applying the function G. So this cluster set is actually the set of accumulation points in the image of the function G. Obviously, and the second condition is that this is called the cluster graphics, has zero measure. That is what I am going to call it area. So the second condition is that the cluster graphics has 0 area, measured with the Hausdorff two-dimensional measure. And the cluster graphic is used collecting all the possible cluster sets. Now, if we can imagine the graphic of this meromorphic function G, the cluster graphic is the boundary of this, the boundary of the graphic. That is what's happening close to the set E. Something very important about this cluster set is that if the function is continuous at the point set, then it has to, the cluster set is just a point. Okay, perfect. So the cluster set is a single point when the function G has a continuous extension on set. For example, if we take this classical function, the exponential of 1 over z, this function is holomorphic in the complex plane minus the origin, but the cluster graphic has infinite area because the cluster set at the origin actually corresponds to the whole Riemann sphere. Another example that I really like is that, for example, if we take the set E with the 0 and a sequence which is converging to 0, the classical one, and we take this holomorphic function, it has poles and every point 1/2, 1/3, 1/4, and so on. Then the cluster set on these points is only the infinite point, the point and infinity, because it is a pole. And a very natural question is how big can be this cluster set? This cluster set already has infinity, and it has another points, not infinity. And I suspect that this set is the whole Riemann sphere, but I'm not completely sure. So it's a very interesting case, but this set has to have positive area because if, well, that is obtained after, that is deduced after applying the Chirka result. And well, now some applications. This Chirka result has a very nice applications to removable singularities. So for example, using the classical setting, if we take an open set in the plane and a closed set, which standard Hausdorff measure with the Gauss function omega squared is equal to 0. Well, we take this Gauss function rather than a linear function because we don't want to work with trying to measure the three-dimensional Hausdorff measure of something larger than 2. So we have this condition just to be sure that everything works fine. And given a countable set, that's very important. We remove a countable set from E and take a function which is continuous in the complement of this countable set. And it is holomorphic in omega minus E. And we request this condition. This condition is very similar to the ω-Hölder condition, but for the ω-Hölder, we have to put a positive constant here, which is completely independent of the point C. In this case, we're not requesting that, we're not putting a constant in this place, we're only allowing that this limit goes to infinity. Well, it could be finite, we're not requesting to be infinite, but it is not uniformly bounded with the variable of C. The other point is that we are just requesting that this condition holds for the point C in the complement of X. That is, this limit can be infinite in the point X, in the points of X. And under this condition and the extra part that, for example, the cluster set are connected, have 0 area, and have connected complement, then G has a holomorphic extension on omega. Now, this result is very special because two things. Since the set X is countable, then it can be dense on A. It can be dense on E. And so we are allowing that this limit, the superior limit, can be infinite on a dense subset of E, which is something quite special. Well, as I say, the countable set may be dense on E. The classical Hölder condition and I explained, means that this superior limit has to be uniformly bounded. We remove that condition here. And the classical, so for this case, we have a very nice result. But it has a problem. And the problem has to do with this Hausdorff measure. Here I am using the omega square. So if I recall the classical Dolzhenko results, they require that the Hausdorff measure T times omega is 0. And this condition is weaker than the condition that we are requesting now. That here we're using omega square, and this condition is weaker. On the other hand, for the Dolzhenko result, the Hausdorff measure is calculated using open covers. And now we are calculating the Hausdorff measure using any kind of cover, an arbitrary cover. Well, let me get a proof of this result. And the proof is very beautiful. Well, firstly, I am going to assume that the set E is not empty. If it is empty, the function is already holomorphic everywhere. So it's not an interesting case. Using Chirka's theorem, we only need to verify that the cluster graphic has 0 area. Why we need that? Because when we request that the leaf soup is bounded, we automatically have that the function, that the cluster set, that the function G is continuous on the points E minus X. So if it is continuous, the cluster set is only 1 point, so it is not an interesting case. So, well, in any case, we only need to verify that the cluster graphic has 0 area. To do so, we define this function. It's a very funny one. And the first step, which is relatively hard, is to prove that this function is bounded for every point C. This can be verified in the following way. We know that the limb soup, when set goes close to C, no, to he, sorry, when set goes close to he, the limb soup of this fraction is bounded. So we know that this condition is bounded very close to the origin. Well, very close when this number, this distance is bounded when this distance is very close to 0. When we are far away from 0, if we substitute this inequality by some constants like delta is less than equal to this part, where we will finish working with a compact set because E is closed, and then we remove another closed set. Well, this set is closed, and then if we put the condition delta less than equal to z minus x he, we finish working with a compact set. Therefore, this function has to be a maximum. Then, well, making some operations, we can prove that this value is always finite. That's very important. And it implies that E minus the neighbor U is the union of all these level sets. Since we know that this Hausdorff measure is equal to 0 for E, then this Hausdorff measure is equal to 0 for F lambda. And therefore, and so given any epsilon, which is strictly positive, this set can be covered by disk of radius Rj, centered at some point, and such that this sum is less than equal to E. Sorry. Perfect. So now we are going to begin to work with the graphic. Well, we have to calculate the size of the cluster graphic. So we try to calculate the graphic of G over this set. Maybe if I draw a little here, this graphic is going to be something like this. Let me draw this. I'm sorry, I'm very bad for drawing. But it's something like here. The graphic of the function, that is the graphic of G, is going to be contained. This graphic is going to be contained in a square where the base is going to be the disk, and the height is going to be given by these conditions. Since we know that phi is bounded by this term, and we put this less than equal to lambda inside, we're going to have that the distance between the values of the function g and z and the center of this point is going to be bounded by lambda times omega squared, well, lambda times omega this side. So the size of this part is going to be lambda omega. Now, if we calculate the diagonal, we're going to get this value. This is just the diagonal of a rectangle. Then the graphic of the function g, let's imagine that this is a graphic, is going to be contained in a ball centered at this point, and whose radius is going to be exactly the side of this diagonal. We calculate that. And then we know that the omega Lj is greater than some constants times the radius Lj. So we have this inequality, that's no problem. And moreover, if now we take this inequality, we square it both sides, and then take the sum of all the possible disks. So we know this sum is less than epsilon. We are going to make some operations here, and we're going to get this one. The graphic of G over this over F lambda is covered by closed balls whose radius satisfies this condition. And this condition is precisely the one that we need in order to calculate the second dimensional Hausdorff measure. We only need to make epsilon goes to 0 and goes to very small. We made that operation, and we have that this cluster graphic has 0 area. It's no problem. But then, and that is the important point, we know that this set is the union of all these values, because we indeed calculate that the function phi, it takes only finite values at every point. Then we have that this cluster graphic has 0 area because it is the union, the countable union of sets of 0 area. And moreover, this U is an open neighborhood of X. Then we know that the cluster graphic over E minus X can be covered by a countable union of set of 0 area. Therefore, this set has 0 area. And moreover, since we know that the cluster set have 0 area because of the hypothesis for every point in X, and X is a countable subset of E, then we add again a countable number of set of 0 area, and we have that the cluster graphic has also 0 area. And therefore, Chirka result automatically implies that the function G has a holomorphic extension over the whole open set omega. Let me close this graphic. Where is it? Here is it. Yes, because I don't want to carry this graphic everywhere. Perfect. And voila. And then we have this result, that this is the first very easy deduction from Chirka's result, about removability of sets whose area is very small. Now, even when this result is very beautiful because we are working, I really like this result because this condition is only requested in the exterior of a set which can be dense on E. What I don't like it is that this Hausdorff measure is calculated using omega squared, which is not the classical Dolzhenko result, as I say. So one thing that we can do is try to change this value. And yes, we can change the value, but we have to sacrifice. Right now, we have to sacrifice this second hypothesis that this condition is only need to be calculated in the exterior of the set X. Oh, well, let me present the result. It's a second theorem. In this case, well, the classical says we have an open set in the complex plane and we have a relatively closed subset E. In this case, we request that the open Hausdorff measure is equal to 0 for non-decreasing upper semi-continuous function. Yes, I need this condition that omega is now upper semi-continuous. Well, this condition is because I don't want to work with three-dimensional measure, which is always going to be 0, so it's not interesting. And voila. Then now I have here in this upper part the normal condition used by Dolzhenko. But well, then I consider an holomorphic function G. I assume there is an H which satisfies this condition. well, the limb sub is bounded by, is finite, but this is bounded by a constant. This is not really a constant. This value depends on the point C. It's not if I will be working with the Hölder condition, these constants will not depend on phi, so it will be uniformly bounded. But now I am removing this condition. But this is something completely new for myself. Well, I work in this condition, and then I have that the function g has an holomorphic extension on omega. Now, here I am not requesting to begin with that the function omega is equal to 0 at the origin. So if omega is not equal to 0, then this is the classical one-dimensional measure, Hausdorff measure. And if omega is equal to 0, then I am working with another conditions. But the condition that omega is super semi-continuous also means that omega is continuous at 0, at the origin, sorry. Omega is continuous at the origin. Therefore, when omega 0 is equal to 0, the function g has to be continuous, and h is a continuous extension of g. Otherwise, the function g could take any value. Okay. The thing that I don't like here is that I need to request this condition. That is, well, so far my students and myself, we have not been able to remove this condition. That is, to remove the condition that we request that this inequality holds for every point on E. That's something that we will want to remove. We have some particular case, but it's not for an arbitrary E, it's for a special one. Let me show you in the following theorem. If we use the same hypothesis than in the previous theorem, but we assume that G is singular at every point on E, that is, G has not holomorphic extension on any open set that meets E. And moreover, we suppose that the identity 2, that is the identity which is bothering me, this one, only holds for points in a subset of E, then this set cannot be too large. The difference between E minus X has to be dense on E. And moreover, if we assume that X is a G delta subset of E, then E minus the closure of X has to also be dense on E. That is, X cannot be that large. If the identity 2 holds in a set E X, the set E X has to be really, really small. Oh, by the way, just something that I just forgot. As I said at the beginning, when I arrived to the Department of Mathematics, I was interested in complex analysis and general topology. At the end, I finished my PhD in general topology. So I am also in love with this kind of sets which are not closed and open, but those are special. And G delta sets are very special sets. But just a small observation. But let me show just how this theorem 2 is proved. The proof is very beautiful. It's very simple. It's really, really beautiful. It's very complex because we need to do a lot of calculations, but the ideas are very simple. So the first idea is the following. We know that the function g is holomorphic in the complement of E. But since there are two cases, that is, well, the function g has holomorphic extension, it has unique holomorphic extensions. If it has holomorphic extensions, those holomorphic extensions are unique onto open subsets of omega. This happens because two conditions. In the first condition, when omega 0 is equal to 0, that is the Hausdorff length, or the one-dimensional Hausdorff measure of the set E is equal to 0, then the complement of E is connected. So that automatically implies that any holomorphic extension of G has to be unique. And in the second case, when omega 0 is equal to 0, then the function G has a continuous extension. That is, H, as I say, is a continuous extension of G, and therefore any holomorphic extension is unique. Now, I am insisting that the holomorphic extension is unique because that allows me to assert the following. There has to be a set F contained in E, which is the smallest relatively closed set, such that G, well, the holomorphic extension is singular at every point of F. That is, I extend G as far as I can until I hit all the possible singularities that we could have. Since the extensions are unique, the set which contains all the singularities exists. And moreover, I am going to assume that this set with all the singularities of G is not empty. If it is empty, well, the result is automatical. And now, once I have this set E, I take a compact disk of radius, some radius delta, and center and some point of in F, such that this disk is really small. That is 2 times the radius is smaller than the distance from his zero to the boundary. I just made this condition so that I can make the calculations in an easy way. And then for every point in this intersection, notice that this intersection is compact because it is closed and this is bounded. This thing is compact. For every point here, I calculate this function. It's very similar to the function that I was using in the previous proof, but now it's very difficult to prove that for every point G, for every point Y, this function is bounded. And it's very difficult because the supremum is not calculated only on the points which satisfies this lower condition. The supremum is bounded by this, is calculated on this set, which is open. But this is open, this is closed, this difference is open. So, well, in any case, it becomes even more difficult to calculate that this function is bound, is always a finite value. It's possible to do it, but we can do it, that's no problem. It takes 3 pages, no, sorry. It's only 1 page in the paper, but well, believe me that this function is finite for every point. So this compact set is the union of all these level sets. That's what I wanted to do. And moreover, the closure of this level set is contained here. To begin with, I am not sure whether this set is closed, but I take the closure and this is contained here. Okay. So this compact set is the union of a countable number of closed sets. That is the important part. Then if I use the bare category theorem, I know that there is an index such that this closed set has not empty interior with respect to this part. That is the beautiful part when we have to use the general topology. That's why I love these G delta sets, because there we have the bare category theorem, but in any case. Now we know that this set has not empty interior with respect to this intersection, this compact set. That means that there is a disk. Well, it doesn't matter if I take an open disk or a closed disk, but in any case, there is a disk we center at some point in F such that this equality holds. That is, this is part of the interior. By definition of the interior, this equality has to hold. It's different from 0. Therefore, this set is dense in this another intersection. Now, why is that important? If I look back, the way that I define it, the function phi, I know that f lambda, well, everything has to be calculated of f lambda. But in f lambda, I have this inequality. And therefore, this fraction has to be strictly less than lambda. If I accommodate the terms, I'm going to get this inequality here below. And this inequality, well, now I have a lambda which is constant. It's a normal constant which is not depending on set, is not depending on y. Well, as long as set belongs to this set and y belongs to this another set, and I have this condition. But this is a Hölder condition. Well, it's almost a Hölder condition, because if I will want to apply the classical Dolzhenko's theorem, I will only need to put here f instead of f lambda. but I know that F lambda is dense here. Then I only, well, since I know that the G hat, but it's not G hat, it's G bref, is holomorphic in this difference. This measure is equal to 0. And if I use a variation of Dolzhenko result, I will have that G has an holomorphic extension onto the disk D. But then I have a problem because I begin with the assumption that G is singular at every point of F. Therefore, if F, the set F is not empty, I have a contradiction. Therefore, G has to be singular, G has to have an holomorphic extension onto the whole set omega. Now, here we have the second problem. I need to prove this variation of the Dolzhenko theorem. So let me state this variation. It is a classical setting, that is, I have an open set, I have a relatively closed set, I know that this measure is equal to 0, as in Dolzhenko results. I have a function which is holomorphic in the complement. It's exactly in the previous page was D minus F. I was applying that. And I assume that there is a function which is defined in a countable dense subset, sigma of E, such that I have this inequality. But now set belongs to the complement of E, and he only belongs to set. It's very similar to the Dolzhenko result, but in the Dolzhenko result, I have to write E here instead of sigma, sorry. Then if I have these conditions, then G has a holomorphic extension on the set omega, and I say this result automatically implies that the theorem 2 is true. Well, then I have a problem. In order to prove this Dolzhenko theorem, I need to extend G and H onto the set E. And so I need to use the variation of another result. So I need to prove the variation of the Kirsch-Brown theorem, which is saying that under the same hypothesis that the lemma 1, the function is locally bounded. That's just a very simple result. But besides this, if omega of 0 is equal to 0, then G has a continuous extension which coincides with H on sigma, and that the following identity holds for all the points. And then this result is the one that I can use in order to obtain the Dolzhenko variation, to apply the Dolzhenko theorem. Now, just an observation. In the hypothesis of my original theorem, I requested that omega is super semi-continuous. I will be really happy if I can get right of this condition. But this condition, I never used this condition in the proof of theorem 2. Moreover, I never used the condition that omega is super semi-continuous in the proof of lemma 1. What I need the condition is for the variation of the Kirsch-Brown theorem, because the upper semi-continuity plus the fact that omega 0 is equal to 0 implies that omega is continuous at the origin. So it seems to be that I am not going to be able to get right of this condition. I would be very happy if I could get right of this condition, because just I don't like that omega is super semi-continuous. It's just a personal thing. But well, in any case, putting everything together, my student and I were able to prove this result. Well, unfortunately, my students cannot be here because of the pandemic. He has to be back at home, and he doesn't have very good internet connection. But well, we have this result. Then, okay, I am going to hurry with the applications. Now, the most beautiful application that we can think about this theorem is the following one. If we take a staircase, the double staircase function, that is, if we take a measure in the real line, a complex Borel measure with finite total variation and no atoms, that is, the measure of any point is 0 for every x. If we assume that the support has interior and that this Hausdorff measure of the support is equal to 0 for some omega with these properties, Then we have that those are some kind of partial derivatives, and I'm going to explain why. That these partial derivatives of the function of the measure omega, one of these two has to be equal to infinity. And this has to be equal to infinity in an infinite set, which is uncountable. Now, why I call it partial derivatives? Because, well, fractional derivatives or partial derivatives, because if I take the usual one linear Hausdorff measure, that is, if I apply just the absolute value here, then I will have the derivative with respect to the Lebesgue measure. But in this case, if I take a measure which is not the linear one, which is, for example, the fractional 1/2, I can still have this kind of inequalities. And the way to prove this result is the following one. Well, as usual, if I take the measure, I construct this function, measuring the set from infinite to x, which is a continuous level staircase function. And it is continuous because there are not atoms, that is, no point has positive measure. Then I take the intersection of all the closed sets for which f is locally constant in the complement of this closed set. I made this trick for the following reasons. Firstly, I will have that this set is not empty because the function f is not constant. It is uncountable infinity and has not isolated points. It has not isolated points because, again, f is continuous. So that E minus any countable set has to be dense on E again. Moreover, since E is contained on S, by hypothesis S has empty interior, we have this condition. And by the same reason, we have that this measure is equal to 0. Now, once as I have this function x, I just take classically the f of the real part of set. This function is continuous on set. It's holomorphic. It's actually locally constant in the complement of this, this product. And it has to be singular at every point here. And it has to be singular because otherwise I will have an holomorphic extension and I will have that f is constant, but I know that f is not constant. That's why I made this construction. And I take the set of points, I take y, the set of points for which at least one of the inequalities in the hypothesis holds. Let me put these conditions, is one of these two inequalities holds. So, well, if I apply this condition, I have that. That is the supremum limit has to be finite. And, sorry, it seems to be that my connection internet is failing again. Well, I hope that everybody can hear me now. So if I suppose that the set y is finite or countable, then I have two conditions. The complement of y multiplied by all the imaginary x, so that is the set x has to be dense and G delta in my original set of singularities. And moreover, this Hausdorff measure has to be equal to 0. But then theorem 3 yields a contradiction, because under this condition, the closure of x is equal to the whole set of singularities E, and that cannot be possible, because the theorem 3 tells me that x has to be small. It cannot spread along this set of singularities. That means that y must be uncountable infinite. And with this condition, I automatically break the part that x, that the closure of x is equal to E. And therefore, we have this application. Then again, well, these kind of results are just dedicated to one complex variables, is the kind of things for which I come to the Department of Mathematics. I really fell in love with these kind of results, and I am still in love with this kind of results. But well, that will be the problem that I wanted to present. Thank you to everybody. In the name of myself and my students, thank you all for hearing our conversation. Thanks.
Okay, thank you very much, Professor Santillán Zeron. So questions. Well, I have some questions. Why the name Devil's staircase functions? Why that name?
Because it's a devil function that is because it's locally constant everywhere. So originally the people begin to when the field of real analysis was settled on, it was thought that every function which is constant almost everywhere, that is, whose derivative is equal to 0 almost everywhere, has to be equal to 0.
Okay.
Or for example, or it has to be like a step. If you have the step function, the derivative is 0 everywhere, but it is not continuous. So people were thinking that if you add continuity plus the derivative is equal to 0 almost everywhere, the function has to be constant everywhere.
Okay, thank you.
It is a devil problem. Well, sorry.
More questions, comments? It seems that Professor Michael Range wants to make some comments, but the problem is the sound. The microphone. Professor Range, could you open your microphone, please?
It's not there.
Okay.
No, the microphone is not working. Can you?
Yes.
Professor Range?
Yeah.
Okay.
Can
you now?
Now
yes,
it's
indeed.
Yeah, okay. Well, I was going to comment about the devil's function. I never heard that particular name, but I have seen this function because, I mean, it's sort of this classical one variable result in calculus that if a function has derivative 0 everywhere, then it has to be constant. But the trouble is that that result involves a completeness of the real numbers. And, you know, what I think is a devil's function, I suppose, is a function that, you know, has 0 derivative at all the rational points and is not constant. So that's basically what's going on here, right?
The second name, the more usual name is Cantor's function. Yes, but I like more this name. It's more attractive. Yeah, the first example is due to Cantor, because it is constructed as a function which is constant in the complement of the Cantor set.
Okay.
So in this case, the support of this measure has to be the Cantor set, and well, there is a lot of deductions about that.
Okay.
So, may I ask, when was the term devil's function introduced?
Let me look for it, and I will let you know tomorrow.
Yeah, okay, well, just
I had the impression that it was since the beginning, because it is really a very strange function.
Oh, yeah, I understand the name, sure.
Tomorrow, before you talk, I will let you to know the answer. It's no problem.
Very well, thank you.
Okay, more comments, questions? No? Okay.
Well, I may just add one more comment here. I was very much surprised and taken by seeing how Hölder continuity with a more general gauge function, you know, is a very important concept here in this particular mathematical problem. And I just want to recall that in the case of solution operators for the Cauchy-Riemann equation, I mean, already in the one-dimensional case, the Hölder regularity of the solution operator is a very important way of measuring, you know, how the operator regularizes a function. And
yes, indeed, yeah, and actually, and that is a classical way to construct the singularity singularities is just to take the Cauchy kernel and integrated it with a very nice measure. But the problem is how to prove the Hölder, a Hölder condition of this in the Cauchy integral. That is, it's not easy when the set is very teeny. It's not easy at all.
Okay.
Okay, thank you.
So, okay, thank you. More comments? More questions? No? Okay. So once again, thank you very much, Professor Santillán Zeron.
You're welcome.
See you tomorrow in the second day of this set of talks. Thank you very much to all the participants.